Does anyone have any questions before I jump into the new material? All right. Well, feel free to type them down in the chat. Also, I want you to go ahead and type your first and last name into the chat. So I'll have that for roll for today. I'm basically going over the same thing that I covered in lab on Wednesday, Shonda. So, but I might actually go a little further because I'm not going to do some of the derivations. I'm going to do even fewer derivations, let's put it that way, but I'm definitely doing the first part, which I think is most important and probably everybody will benefit from seeing even a second time. So you might want to stick around at least for the first part. I am, as I said, still trying to work on the face-to-face practice test. Uh, Hopefully I'll get that finished tonight. Worst case scenario, it might be tomorrow, but I have to basically select a portion of the chapter 7 or chapter 24 material that is consistent with what I will be testing people on the face-to-face test. And since my 242 class, well, I'll take it the week we get back, I can't allow myself to go beyond what I've covered as of today at the end of the day. So anyways, I'll get that done and I will send you an email when it's done. Uh, I'm going to go ahead now and share my screen. It looks like most people are going ahead and chatting maybe their first and last name. That I definitely need y'all to do, so go ahead and do it if you haven't finished yet. And I've already got some of the notes put up on here already, specifically because, as I was telling Shonda, I am wanting to not use some of my lecture time for actual derivations. Specifically, there's formulas that you guys probably already know, hopefully from lab, and when you're trying to find the equivalent resistance of a bunch of resistors in series and the equivalent resistance of a bunch of resistors in parallel, well, there's similar formulas, but they're exactly opposite for capacitances when they're in series or parallel. So I derived those last time in my lab, but I think working problems like I was doing there is just as helpful. So I'm not going to bother doing that. And I'm just got them written down right now. So let me also turn on the chat in case anybody sends me an answer. Okay, so I've got the chat open. So you notice right there, I've got Gauss's law. That's the first thing I put up there, and that's because today I'm going to teach you the what I call one of the two paradigms that are so important for the 242 physics course. The 242 physics course has one paradigm where you either use Coulomb's law, hopefully not, or Gauss's law, hopefully so, to find the electric field of a certain charge distribution, specifically a certain charge distribution that has a positive charge separated from a negative charge that we can consider a capacitance and therefore calculate the capacitance of. So the paradigm step one is use Coulomb's law or Gauss's law to compute the electric field for a certain charge distribution setup. Step two is use delta V equals a negative integral of E dot dl to calculate the potential difference, i.e. the voltage difference between the positive side of the charge configuration to the negative side of the charge configuration. If you actually go from negative to positive, that will give you a positive change in voltage, and that's really what you want. But if you do the other way and you end up getting a negative, you can just erase the negative and right answer. Okay. So that was step two. And then step three is to take your results that you got for this new voltage and divide the charge of the configuration, which basically any kind of capacitance will have a certain amount of positive charge on one part and the exact same amount of negative charge on the other part. And what I'm saying is you take that charge with no sign on it and divide it by the voltage difference between the two parts, and that gives you the capacitance. So that's your three-step paradigm. So again, I'll just repeat the three steps. One, calculate the electric field using Gauss's law or Coulomb's law. Two, calculate delta V equals a negative integral E dot dl between the two charge distributions. Three, use C equals Q over V to calculate the capacitance. So I'm going to start off showing you that. I've already written up here, in addition to that, I've written the definition of capacitance. You can see C is equal to Q over V. And I'm letting you guys know that unit-wise, that means the units for capacitance are coulombs per volt, and we define the coulomb per volt as 1 farad. So you see the FARAD with the basically the abbreviation is just a capital F. Then the formula, notice how it's reversed here. The formula for the equivalent capacitance of any number of capacitances in series is 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus dot, dot, dot. Similarly, if you have a bunch of capacitors in parallel, the equivalent capacitance of that bank of parallel capacitors is C1 plus C2 plus dot, dot, dot. And then finally, there's a derivation your book also handles that tells you the amount of energy stored in a capacitor. And I usually remember just the first one, which is U is equal to 1/2 CV squared. And the reason why is it looks just like 1/2 KX squared. It looks just like 1/2 MV squared. And you'll later find out it looks just like 1/2 LI squared, which is the second paradigm that we're going to study once we get into magnetism. But the main thing is that 1/2 CV squared, since it's mathematically equivalent to 1/2 KX squared, and since the 1/2 Li squared is mathematically equivalent to 1/2 MV squared, you can see that when a capacitor and an inductor are put in a circuit, the energy is going to slosh back and forth between electric field energy and magnetic field energy, just like the energy sloshes back and forth between a spring's potential energy and the mass on the spring's kinetic energy. Okay, so let's go ahead and get started with the idea of doing one of these things that I call a paradigm. So it's basically just a process that we go through. And at this point in the semester, it's a really good comprehensive problem that shows us what to do. So, and shows you that shows me that you know a great deal. Okay. So I'm going to draw a coordinate system, and it's a three-dimensional coordinate system. And that's it. This is my x-axis, this is my y-axis, and this is my z-axis. And what I would like to do is imagine a three-dimensional, actually, I don't want to go quite that far. Let's imagine a two-dimensional infinite plane. So I'm going to say, let's start right here. Right here. And what I'm imagining is that this plane will go on forever that way and that way. And of course, also this way and this way and this way and this way. And of course, this last corner as well, but it's a little harder to show like that. I'm going to say that this particular plate has a uniformly distributed charge, sigma. So what we're asking here is what is the electric field caused by a uniformly charged. Now you can see why I had to go to the next line. Uniformly is probably not going to fit in that line. Infinite plate. Okay. So that's the actual problem we're trying to solve. We're going to use that because it turns out that when you make a parallel plate capacitor, you use two plates and you put them so close together that basically if you're in the middle, you're so close to either plate that the distance to the edge of either plate is 10 times as far at least. Okay, that's sort of our rule for if we're talking about things being infinitely far. We at least need a factor of 10. Usually a factor of 100 is better, so that's what we're shooting for here. Obviously, like I said, in this case, the first step is to find the electric field. So this is step one of the paradigm. I'll put a little red one here just to remind us that this is step one. Uh, what we have to do is, in this case, I'm going to use Gauss's law. So our solution is going to entail this. The closed integral of E dotted with dA is equal to the enclosed charge divided by epsilon naught. Okay. We're slowly getting to the point where I shouldn't be showing you all the steps. I should be more like showing you what you would do in a real test situation. I'm probably going to do a bit more of showing of steps for this one particular one, but I'll stop thereafter. But hopefully it'll be enough to have seen it this time to where you'll finally be able to make some sense of it. So the number one rule when you go to use Gauss's law, like I'm getting ready to use it, because Gauss's law is Gauss's law, not Gauss's helpful hint that sometimes works. It's a law, but when we use it to solve for the electric field, which is actually the integrand in the left-hand side, uh, we're doing some very special stuff, and that only works if you have certain symmetries, and the symmetries are generally infinitely thin, infinitely long lines, or you don't have to be infinitely thin. You can just be infinitely long cylinders, or infinitely large planes, or a sphere. So those are really the 3/4 symmetries that you have to have if you wish to use Gauss's law to compute the electric field. So in this case, we have an infinite plane. And what we have to do is we have to have some knowledge that we've gained from working with Gauss's law, or more formally, before that, we worked with Coulomb's law to figure out how certain charge distributions created electric fields of certain shapes. And what I mean by a certain shape is you should always be able to imagine for a certain charge distribution, what would a surface look like on which the electric field is a constant. So if you can imagine this infinitely long, large, flat plane that has in every square millimeter the exact same charge as every other square millimeter, hopefully you can think of the types of surface that would actually have the electric field be constant on it. Now, if you remember, what we discovered was that electric fields are perpendicular to equal potentials. Therefore, if you find a plate or a plane of some sort, some shape that has the electric field constant on it, then that's basically the definition of a equal potential surface. And the equal potential surfaces are perpendicular to the electric field. So that also tells us that you got to find a surface on which the electric field is constant and on which the electric field is perpendicular. But you don't have to treat that like an and, you can treat it like an or. So you can say or it's perpendicular to the surface, or it's constant on the surface. So does anybody is anybody able to look at this particular infinite plane and tell me any kind of shape on which the electric field will be a constant? Because that's what our Gaussian surface has to be. The Gaussian surface always has to have some number of surfaces all have the electric field constant and perpendicular to them, and all the other sources have to have the electric field uh, more or less parallel to the surface so that the dot product becomes zero. Okay, so can anybody think of a shape, a plane of some sort, or a surface of some sort on which the electric field caused by this plane would be constant? Feel free to type it in if you want to do it that way. All right, so what I am going to do is go ahead and make my hypothesis, and hopefully that'll be enough to help you guys see it. Don't give up though if you're still thinking about it. continue doing so in hopes to finish it. But what I'm going to say is the electric field, E vector, is equal to a piecewise function. And that function, another person coming in, that function is going to be, dang it, God, I really hate this. That function is going to be the magnitude of the electric field, which I suspect is only going to depend on the component or the coordinate z, times k hat, meaning it points upward in the positive z direction, and that is for z greater than 0, and then negative e of z k hat, meaning it points in the negative z direction, and that is for z less than 0. So my argument right there, by calling this the hypothesis electric field, is that I'm saying if you take any surface of constant z, then you have a electric field that will be perpendicular to that surface, and of course will have a constant value on that surface. So what you can do is, and we normally, by the way, use a cylinder. One of my students asked the other day, why couldn't I use a square? And I'm just going to show you, you can. It doesn't really matter. So I can take a purple surface right here that's going to be my Gaussian surface. And what I'm trying to do is show that square surface, it has its center right on the z-axis. Okay, it doesn't have to be that way, but that's the way I tried to draw it. So this axis is going to come down here, or this shape is going to come down here like this, and this. And in fact, you can see it going back here like this as well for 3 dimensions. And that's the surface. And then, of course, it has to go completely through the plane. So the surface will continue back here like this. Okay. And what I'm going to say is if we look at this little, dang it, if we look at this little rectangular slash square box, what we're going to say is the area of this top is just an area A. Of course, it's a cubic or rectangular box, so that means the surface within the box is also an area A, meaning the surface of the infinite plane that's in the box is an area A. God darn it. I'm trying to clean this up a little bit more so you can see. So this stuff back here, you can't really see that well because you're seeing it through the sides of the container, and the same thing back here. So hopefully y'all can get a load of that, if you will. Now on the top, we are going to have a differential area element, dA top, which is just dA times k hat. And then down here on the bottom, we have a dA bottom, which is equal to negative dA k hat. And then I would normally call this outer edge here, I would call it a soup label because it would be the label of a cylindrical soup can, but now I did it rectangular just to satisfy one of my students' concerns. I'm going to say this dA is dA side, which equals a dA times, let's say in this particular case, you can see the dA points in the j hat direction. And for instance, over here, the dA would point in the I hat direction. And over here, the dA would point in the negative j hat direction. And back here, this dA would point in the negative I hat direction. Okay. So that's sort of the only real problem with using a rectangular shape as opposed to a cylindrical shape, because a cylindrical shape has three distinct surfaces: top, bottom, and cylindrical soup label. This one has top, bottom, front, right, back, left. So it's a little bit more problematic, but that's okay. So now we have it. I'm going to go ahead and say left-hand side. So remember, the way we use Gauss's law is we solve the left, we solve the right, we set the two equal to each other, and then we solve for the electric field that's part of the left. And the only way I found that's nice to do that without it, putting fake symbols up that aren't equal to each other and stuff, is just do the left-hand side, do the right-hand side, and then set them equal. So the left-hand side is the closed integral of E dot dA, which now is going to be even more complicated because I'm doing these rectangular spots. But basically, I'm going to say it's the integral over the top of E of Z K hat dot dA K hat plus the integral over the bottom. I'm choosing to do it in a very specific order for a good reason. This is negative E of Z. No, that one should actually be, yeah, that one should be negative K hat dotted with negative dA bottom are, so this is the bottom one, so it's going to be negative dA K hat plus, I'll say, the integral over the front, which would be plus or minus E of Z K hat dotted with dA I hat plus the integral over the right side, which would be plus or minus E of Z K hat dotted with dA J hat plus the integral over the back, or let's call it rear since we haven't spoken for the R yet. So yes, we have spoke for it in the right. Let's say, I'll just say BA for back. Okay, this is again going to be plus or minus E of Z K hat dotted with, in this case, is going to be negative dA I hat. And then finally, it's going to be plus the left face, which would be plus or minus E of Z K hat dotted with negative dA J hat. Okay, so that's like the whole darn thing. Of course, you can see from the dot products, though, that K hat dot I hat is equal to 0, and that K hat dot J hat is equal to 0, and that there's another K hat dot J hat, so that's also 0, and there's a K hat I hat over here as well, and that's equal to 0. So you see, you really get no terms except for the top and the bottom one. And for the top one, what happens is we're evaluating this integral. It's actually a surface integral, and we're evaluating it on z, which is the height or the z coordinate of the top of the surface. And that's the variable that E depends on. So it's just going to be E of Z out in front of the integral. And then we're going to have an integral of dA. And then, of course, it's going to be K hat dot K hat. And this is just 1 cosine 0 degrees, which is 1. And then the same thing here. Oops. The same thing here, I'm going to get E of Z. Notice the two negatives cancel out, and I'm going to get dA K hat dot K hat, which again is equal to 1. So ultimately, the entire left-hand side just becomes 2. Remember the area over the box. In other words, if I look down along the z-axis, the area that I would see is A. So I'm going to get E of z times A plus E of z times A. So this is going to be 2E of z times A. So that's what my left-hand side is. I don't like how that turned out. Everything about it was ugly. So E of z A like that. Now I'm going to do my right-hand side. And I actually didn't change colors. Now I'm going to do the right-hand side. And the right-hand side with the drawing should tell you or should be able to be solved very easily. It's Q enclosed inside of that little box over epsilon 0. Can anybody tell me what Q enclosed would be? Let's zoom in and then hopes that you can see everything you need to see. Anybody tell me what Q enclosed is going to be now? Micah, I answered a cylinder earlier. Cylinder would have been fine. We would orient the top of the cylinder parallel to the top of this box, and the bottom of the cylinder would be parallel to the bottom of this box. But instead of having the rectangular sides, we would just have that cylindrical side like that. So yeah, that would have worked. Anybody have what the Q enclosed is? So the key to getting you enclosed is you guys got to know this one part. I'm going to write it again. I'm kind of concerned about how many people don't seem to be getting this. But dq is either lambda dl or sigma dA or rho dV, where rho is the charge per unit volume. That's a type of charge density. The dA is a surface area, so the sigma is a charge per unit area, and the lambda dl, the dl is a line, so the lambda is a charge per unit length. You've got to know these to be able to do any of the integral problems as well as to make sense of the Gauss's law problems. So can now that I've given that hint, can anybody tell me what Q enclosed is? Still nothing. Okay. So Q enclosed, when you have a density of some sort, this, for instance, is a infinitely large plane with uniformly distributed charge on it over 2 dimensions, right? There's a third dimension, but it's infinitesimally thin in some sense. And because of that, it's a two-dimensional object. So that should be your first thing to make you think, oh, well, sigma is probably the charge density that we're going to use. And then, of course, you look up here and see that literally on the diagram, I have a sigma. Okay, so that should not have been a problem. So I also made a point to tell you that the area there was A. So clearly, what you're supposed to say is Q enclosed is sigma A. And then the right-hand side just becomes sigma A over epsilon naught. So now we have the right-hand side and the left-hand side solved. So I'm going to say left-hand side equals right-hand side. You guys got to get this stuff because this face-to-face test that you get when you come back will definitely include Gauss's law problems, and you've got to be able to do that. And in fact, it'll include the Gauss's law used for these for these capacitors. So the left-hand side we found was 2E of ZA, and the right-hand side we found was sigma A over epsilon naught. That shows you that the A's cancel out, and we ultimately get that, using our hypothesis again, we get that E is equal to sigma over 2 epsilon naught K hat for Z greater than 0 and negative sigma over 2 epsilon naught K hat for Z less than 0 and that's what our electric field is. Notice that when you treat the plane as infinitely large, the electric field does not decrease the farther you get away from it. It's a constant no matter, quote unquote, how far you are away. Of course, that only applies when you can keep assuming the plane is infinite. So if you get such a distance away that you're closer to the edge than you are to the nearest part of the surface, obviously, well, you'd be warping space-time, but anyways, that would be a problem. But the main thing is, like I said, if your distance away of closest distance, that is, from the plane is less than a factor of 10 smaller than your distance to the edge, then it's no longer really reasonable to call it an infinite plane. Okay. But you can also see that this electric field, if we make a plot of electric field versus distance, it has our boundary condition that's I've been talking to you about. So for instance, if we go up here, uh, we get sigma over 2 epsilon naught is the magnitude of the electric field. And this is for, I wrote R, but really I should have wrote Z. So for a positive Z, the electric field is a constant. And then for a negative Z, of course, the electric field is also constant, but it's constant down here at the negative side. Still the same magnitude, but it goes like that, and this part sigma over 2 epsilon naught with a negative sign. So you can see the discontinuity, which is really this measurement from here to here, is equal to sigma over 2 epsilon naught minus negative sigma over 2 epsilon naught, which is just sigma over epsilon naught. That's a fundamental fact. Okay, that's something that's one of the boundary conditions of Maxwell's equations. It basically says that the perpendicular component of an electric field is only discontinuous if there's a surface charge, and then its discontinuity differs by sigma over epsilon naught in going from one side of the surface to the other. And that's what we see here. Okay. Now that we have that, we got to go ahead and figure out what the electric field is for a parallel plate capacitor. So now, what is the strength of the electric field between a infinitely large, whoa, no, between an infinitely large plane of uniform charge density positive sigma and another of negative sigma, a distance d away. Assume, well, no, I'll just leave that part off. So now that we have the electric field strength, I'm going to draw a parallel plate capacitor, and I want us to figure out exactly what the electric field is between the plates of that parallel plate capacitor. So I'm going to put two plates next to each other like this. Here's one of the plates. It has a total area, let's say A. and it has a charge density sigma. What that means is the total charge would, of course, be, and should be a negative sigma, by the way. Actually, let me do it like this. Negative sigma. And what that means is if you actually wanted the total charge on this place, it'd just be negative sigma times A, which is what I'd call negative Q. Okay. Now the other plate is doing the same thing, and I should probably stick to the same color I was using there. So roughly like this and that. And you can see they're identical plates in terms of their size. You might have a wire sticking out of this one, and you might have a wire sticking out of this one. And in fact, you could imagine a battery of voltage V establishing a voltage difference between the plates. And what's ultimately going to happen is this left plate will have a charge of plus Q, and this right plate will have a charge of negative Q, and this distance right here is just plain D. Okay? So what I've got to do is figure out what is the electric field strength between them. So I'm going to now that you've seen it in a two-dimensional representation of the three-dimensional object, I'm going to draw it in 2 dimensions so it'll be a little bit easier for us to make some sense of. So this is going to be like my y-axis, and this is going to be my x-axis, and then this right here is going to be my positive plate, and let's say this right here is going to be my negative plate. So this distance right here is D, and this distance right here is 0. And again, for the record, this one will be minus Q, and this one will be positive Q. Okay? So first off, I want you to think for this dot right, let's say this dot right here. What is the magnitude and direction of E field due to the positive plate? So I mean literally just the positive plate. So can anybody give me an answer for that? It might help you to look back here and see what our results were. So you can see in the red box, that was the results I found for an infinitely large plane. And what I've done is I've tried to put the two plates so close together that anywhere between the plates, other than at the very, very edges, you can assume you're infinitely far away from the edges, and therefore the plate's like infinitely large. Okay, so look at that. Now, can anybody tell me the direction and the magnitude of the electric field due to the positive plate? Completely forget about the negative plate right now. Just think about the positive plate. I'm also going to do it in these locations. Anyone? Micah, how about you, buddy? You normally got my back a little bit here. Sorry to call you out like that. All right. Well, according to the derivation we just did, the electric field strength for any infinite plane is. Gotcha, no problem. The electric field near any given plane, again, meaning the edges of the plane are really far away, always has a magnitude given by sigma over 2 epsilon naught. Okay. Now, the left plate is positively charged, so that means if I put a positive charge at that red dot between them, that positive plate would make it move to the right. So the answer is going to be sigma over 2 epsilon naught, and the direction is going to be that way. Okay. Now let's answer the same question for this dot. Can anybody give me the direction and magnitude of the electric field? Again, just by the positive plate. Completely forget about the negative plate. Let's start off. Can anybody tell me what direction? Yes, that's right, Micah. Uh, that's right, the magnitude. How about the direction? Can anybody tell me what direction the electric field would point on the left-hand side of the positive plate? Completely forgetting about the negative plate. And actually, I think Micah tried to give it exactly. So in this case, if we were on this side, the positive plate would compel a positive charge to move to the left. And in fact, its magnitude would still be sigma over 2 epsilon naught. Now, one more time, can someone tell me in which direction and what magnitude the electric field due to the positive plate would have at this last dot? Start off with the direction. Let's make it easy. Can anybody tell me what direction, that rightmost dot, what direction will the positive plate create an electric field pointing in? In other words, if I put a positive charge there, which direction would the positive charge want to go as a result of that positive plate? Again, pretend like the negative's not even there. That's right, Carly. So the direction over here would also be, and I've been doing it in purple, so I should stick to purple. The direction over here would also be positive to the right. And of course, the magnitude, as long as you're not too terribly far away, and I've sort of exaggerated this D should be probably about 6 times closer than it is on here. But with that in mind, this too should be sigma over epsilon naught. Now I want to do the exact same thing for the negative plate, but this time I want it at this dot, at this dot, and at this dot. So let's say, same questions, but I don't want to put it there. I don't have enough room, but due to the negative plate. So this time we're saying what there, and what there. So can anybody tell me between the plates, which direction will the electric field due to the negative plate point? Right or left? Right or left? Remember, the negative plate means it's negatively charged, and the electric field direction is always the direction a positive charge would want to go. So if I stuck a positive charge in that spot of that purple dot between the two plates, which way would it be compelled to move? Anyone? Yes, very good, Carly. Very good, Micah. So yes, it's going to move. It's going to have an electric field to the right, and I bet you all can guess what the magnitude will be. Okay. What about the rightmost dot? So this dot on the right-hand side, which direction will the electric field point there? You were right, Micah, as was Carly. So again, forget about the positive plate and let's say which direction would it point? Very good. Carly said left, Micah said left. That's exactly right. And then I erased a big swath just because I love it. It makes me very happy to have to redraw everything. Okay, and one last question. How about this dot over here at the far left? In which direction will the electric field due to the negative plate point? Yes, That's very good because it's still attractive to the positive charge would still be attracted to the negative plate, which is to the right. So yeah, it'll be to the right, and this one will be sigma over 2 epsilon naught. Now, the whole reason I did this is so that you'd see what's happening to the electric field in each of those three regions. So hopefully you all put together that E equals 0 out here. Notice they have the same magnitude, but the opposite direction. So the electric field outside the plate on the left side would be 0. If you look at the right side of the two plates, they're opposite direction and equal in magnitude as well. So they're also going to give us E equals 0. But then finally, if we want to know the electric field between the plates, these two both point to the right. So you end up getting a net electric field that is sigma over epsilon naught, not sigma over 2 epsilon naught. So just see how you added them? Yeah, good job, Micah and Carly and everybody else. I know this is kind of complicated, but you guys can do this. I know you can. Just keep up the good work. Keep paying attention. Try to look at a bunch more examples of these Gauss's law problems on my YouTube channel. Do a search for Gauss, Gauss, on my YouTube channel, and you'll find a ton of examples. All right, now that we have that, we have come very close to completing step one. Well, actually, we've now completed step one. So now we're going to do step two of the paradigm. So step two of the paradigm, which I'm writing in blue, I'm writing the arrows for the paradigm in blue. I'm going to separate this from the rest of the problem with a black line like I did before. In this case, I'm now going to ask what, oops. What is the potential difference between the two plates? So that's what I'm asking for. So I wanted to make sure you guys understood when I say the phrase potential difference, we mean the electric potential difference, which is the voltage. Okay. So the solution to this is we have to use this expression, which says delta V is equal to V final minus V initial. Remember, deltas, that triangle there always means final minus initial. In this case, it happens to be equal to the negative integral of the electric field strength dot dl. And we have to remember that that is, in fact, a or line integral or a path integral. So we've got to be very specific about how we do it. Specifically, we either have to use DL. So this is a sentence that you have to have somewhere so you guys can understand this, and you need to put it in your own words. You're going to choose to integrate from one plate to the other in a very specific direction. Because of that, you have to make sure your integral shows that you're integrating that particular direction. And you can do it either that means one or the other, either with the DL, in which case the range of integration would just go from small variable to large variable, and the DL would point the direction you're actually going. Or the other choice would be with the range of integration. In other words, from the initial position to the final position is what your range of integration is, but the DL would point in the positive coordinate direction. Okay. So what I like to do is I try to shoot for a positive quantity. So that makes me a little better at making sure I'm doing my integrals right, a little better at making sure I understand voltage, all that good stuff. So I recommend doing the same thing. But also, if you're in the middle of it and you get a negative, that's okay. If you're taking a test or something, you do not want to redo that. You want to just erase the negative and put it in the next part of the answer. So what I am going to do is I'm going to say integrate from x equals d to x equals 0. And I'm doing that because V at positive Q is greater than V at negative Q. In other words, we know already that the voltage is higher on the positive plate. And if I integrate from the negative plate to the positive plate, then delta V, which is final minus initial, should be a positive. Okay? So this is how I do it. Delta V is equal to the negative integral of, now my electric field, we've already decided, is sigma over epsilon naught, and it points to the right, which is the I hat direction. Okay. Now we've got to dot that with our DL. What I'm going to do is use the DL to indicate the direction I'm integrating. So in this case, I'm integrating in the negative x direction. So I'm going to say, dang it, I hate that. So I'm going to say DL is negative dx I hat. Let me write something on here. Okay, so that was my choice. I chose to indicate the direction of integration with my DL. I'm clearly going to the left because my DL says negative dx I hat. That means my range of integration just goes from small coordinate to large coordinate. So I'm going to integrate from D, or from x equals 0 to D. Okay. Notice that's just a positive coordinate direction. Notice it's exactly the opposite of which way I'm going, but that's okay. That's the way we do a path or line integral. So what I end up getting is the negative times a negative gives me a positive. The sigma over epsilon naught is just a constant. And I have the integral from 0 to D of dx times I hat dot I hat, which you all know is, of course, 1. Now, the integral from 0 to D of dx is just x evaluated at D minus x evaluated at 0. So we end up getting sigma D over epsilon naught, and that's what our voltage difference is. Any questions on that? All right, so we've now completed part 2 of the paradigm. Now we're going to do part 3 of the paradigm, which is usually the easiest of the parts. Okay, so part 3 of the paradigm, oops, use C equals Q over V to compute the capacitance. Okay, so that's the third part of the paradigm. It's really easy. All we've got to do is this. C is equal to Q over D over V. And remember, I already told you that Q, which is, remember, for a parallel plate capacitor or for any capacitor, they have equal but opposite charges, and we just want the magnitude. I already told you the charge per unit area was sigma, and I told you the total surface area of the uh, plate was A. So if you multiply sigma times A, you get Q. So this is going to become sigma A, and then I got to divide that by my actual voltage, which I got was sigma D over epsilon naught. You can see now that these sigmas cancel out, and that's a big fundamental idea. When you solve for capacitance It should come out in terms of geometric things like area, separation, that sort of stuff. There should never be any remnants left of the charge. In other words, you shouldn't have a lambda, you shouldn't have a sigma, you shouldn't have a rho, you shouldn't have a q, any of that kind of stuff in your capacitance. And in fact, in this case, what we see is that we've got epsilon 0 A over D. So the capacitance for a parallel plate capacitor C is equal to epsilon 0 A over D. So that's a parallel plate capacitor. So this is a process that you guys are supposed to be able to do. If you'll notice, the author does not number the results of these capacitance calculations. That means he's not expecting you to use them. He's expecting you to derive them. And then, of course, once you've derived them, you can use them over and over again. But he does expect you to. And usually, at least in the midterm and the final, I have at least one or two times where I ask you to show me all the steps required for you to do uh, the Gauss's law to actually solve for the capacitance. I will tell you that if the space is filled with a dielectric, then, and that's a C there, then we get the following result, which is C is the dielectric constant times epsilon 0 times A over D, or sometimes we absorb the K into the epsilon 0 and we make a new value called just plain epsilon A over D. Both of those are completely correct and acceptable. Okay, we're going to solve problems with that stuff later, but I just want to let you know that's the only difference. If I decide to put in that gap between the positive plate and the negative plate a insulator, and the fancy word for insulator in this course is dielectric. So if I put an insulator in between there, that solves a lot of problems. One, remember we found that 3 million volts per meter, which is the strength of an electric field, will actually cause even air to be a conductor. So if you had an electric field that was as big as 3 million volts per meter between them, then it would be a failed capacitor because the actual air separating the two plates would conduct electricity. So if you fill that air instead with some other insulator that actually can stand up to a larger electric field before failing, then you've made it or you've prevented the capacitor from failing at even higher electric fields. Not only that, you've given it a structure where you can keep the two conductive plates from touching, because often, since you can see that the capacitance is epsilon 0 A over D, you can see that you really want the A to be large to get a large capacitance, and you want the D to be small to get a large capacitance. Uh, A being large is bad enough because these are things that fit inside of little radios or cell phones and stuff like that. But D being very small is also a problem because that brings the two plates so close together that lightning's even more likely to strike. So it turns out you can take and make a really big sheet of, let's say, mylar or some other conductive material like aluminum foil. And then on top of that sheet, you can take and stick a piece of lucite or a piece of some other insulating material that ideally would be able to bend and stuff. You can lay that down on top of the aluminum, covering up the whole aluminum foil, and then lay the other sheet of aluminum foil down, connect a wire to one sheet and a different wire to the other sheet of aluminum. And then you can take and roll it up and fold it up all you want. And because it's got that non-conducting material in it, that's going to keep the plates from touching one another, and it allows you to roll it quite tight. And that's really how they actually make a lot of the cylindrical shaped capacitors that you run into. So anybody have any questions on that? All right, well, let me go ahead and show you yet another one. And this one's going to be for a coaxial cable. So I'm going to use the paradigm to solve a coaxial cable capacitance. Use the paradigm to solve, or actually say to calculate the capacitance per unit length of a coaxial cable with a uniform charge density lambda is equal to Q over L. Okay, you need some information about the individual coaxial cable, so I'm gonna draw that in a second, but right now I just wanted to put that much in writing. The rest we'll get from the drawing. So I'm gonna draw a z-axis, and then I'm going to draw a y-axis, and then I'm going to draw an x-axis. This will be my x-axis, this will be my y-axis, and this will be my z-axis. Now I'm going to draw the inner conductor part of the coaxial cable. So the inner part is just a cylinder. And I'm going to draw this straight down here like that. And straight down there like that. And that's the inner part of the coaxial cable. And when I say coaxial cable, in case you're not familiar with this, that's the big black cord that comes in your wall from your satellite dish or your cable company. Okay. That's the kind of cable they use. Normally, the inner wire is just a little piece of gold wire that's maybe a couple millimeters in diameter. And then a couple millimeters outside of that is actually a screen mesh of stainless steel looking wire. That's the outer conductor. What I'm going to do now is I'm now going to draw the outer conductor like so. And I'm not happy with where that ended up. So I'm going to do it like that. Now I'm going to draw this down here. Now this is supposed to be an infinitely long cylinder. I'm just drawing a small chunk of it. And this should look roughly like that. That was horrible. I didn't like it, but good enough. Okay. So what I'm going to say, and there actually should be another part. So let me go ahead and draw that real quick. Okay. Now what I'm going to say is this goes on forever that way. Okay. Evidently I'm not going to be able to say that in that mode. And it goes on forever this way. And I'm going to say that this length I have drawn is a length L. Okay. So we're going to imagine that this length from here to here is in fact L. And I'm going to draw a Gaussian surface that happens to have that same length. So my Gaussian surface is going to be between these cylindrical wires. like that, like that. Okay. So this one's my Gaussian surface. And the reason I chose that is because I understand that the electric field should point radially outward from the z-axis. I'm going to call this radius R. I'm going to call this radius right here, the little itty bitty radius, I'm going to call that RB. Okay. Actually, that's a horrible looking arrow. And I'm going to call this radius from here to here RA. Okay, so now I've got all the dimensions I need. I know the charge per unit length is lambda. I have my Gaussian surface. I'm going to start step one of my paradigm. So let's start off with solution. So step one, the closed integral E dot dl, or excuse me, E dot dA equals Q enclosed over epsilon naught, find E. Okay, so left-hand side, this is where I'm using it like I would do in an actual test setting. So I know the left-hand side of Gauss's law is always supposed to come out to be an electric field times an area, or some of the terms might be zero. In this case, I know that the electric field is perpendicular to the z-axis and in fact only has x and y components. So the dot product with the top and the dot product with the bottom are going to give me zero. So all I'm left with is 2 pi r times L times E of R. And that's because my hypothesis was E is equal to E of R hat with a subscript C, which means cylindrical coordinates. In other words, it only has a uh, I hat and J hat component. That also could be written as cosine theta I hat plus sine theta J hat. That's actually what RC is. You don't necessarily need that, but it helps. So I now got the left-hand side. It's the area of the soup label, which is, of course, the circumference, 2 pi r times the height, which is L. So that's why I've got that. The right-hand side is easy. The right-hand side is Q enclosed over epsilon naught. Anybody want to take an attempt to answer that? So in this case, it should be lambda L over epsilon naught. Now I say left-hand side equals right-hand side, and I get 2 pi R L E of R is equal to lambda L over epsilon naught. You can see that the L's cancel out, and we end up getting exactly the same thing we got on the first day in chapter 21 when we did Coulomb's law and integrated this result. Specifically, we're going to get E is equal to lambda over 2 pi epsilon naught R times RC hat. That's the electric field. Now I've got to do part two. Delta V equals V final, one more, V final minus V initial, which equals a negative integral E dot dl. Okay. I am going to integrate because I'm assuming the inside has a charge of plus Q. So I'll say and the outer plate has minus Q is equal to negative lambda L. Okay, so I'm going to integrate from R equals the outside one, which is RA, to R equals RB, the inside one. So my integral is going to go like this. Delta V is equal to the negative integral. We've already found out that the integral is, or the electric field is lambda over 2 pi epsilon naught R RC hat dotted with. Now this time I'm actually going to use the range of integration to dictate, to show you everybody which way I'm going. So I'm going to say I'm integrating this from RA to RB. And that means I've got to put my differential length element, DL, has just got to point in the positive coordinate direction, which in this case is going to be DRRC. In other words, it's the positive one. So now you've seen both ways. All right. Now, what's going to happen with this integral is I get negative lambda over 2 pi epsilon naught, and then I get the integral of dr over r times rc dot rc, which of course is just 1, and this is from RA to RB. Yes. Okay, and I'm saying the inside is a positive one. All right, so we've got that, and in fact, what we get is negative lambda over 2 pi epsilon naught, and then the integral of dr over r is the absolute log, or excuse me, is the natural log, and that's going to be RB over RA. Now notice RB is smaller than RA, so this natural logarithm of a number smaller than 1 is going to be negative. So I'm going to absorb the negative and flip the order of them and just say that delta V is in fact equal to positive lambda over 2 pi epsilon naught times the natural log of RA over RB. Now you can see that all of that will be positive. So we've got yet another step of our paradigm solved. If I'd stop erasing stuff. So there's the other step. Now all I've got is step 3. And step 3 is C is equal to Q over V. So for this particular bit, what I know is a length L will have a charge per unit length lambda that gives a Q. So I'm going to say lambda L, oops, I'm going to switch back to purple. So I'm going to say C is equal to lambda L over, now you see you've got lambda over 2 pi epsilon naught natural log RA over RB. And therefore, you can see that the lambdas cancel out. As I told you, capacitance should never have any charge type symbols in it. So we find that the capacitance for a coaxial cable, notice I'm going to divide both sides by L, so it's capacitance per unit length. So the capacitance per unit length turns out to be 2 pi epsilon naught divided by the natural log of RA over RB. And that's it. Okay. Any questions on that? So you've now seen two iterations of the actual paradigm. You can look on my YouTube channel for a ton of them. You can look also in our Canvas modules for week 7 and week 8. It has some as well. Uh, I only have like 3 minutes, so I really don't have enough time to show you how to actually combine the capacitors when you've got a whole bank of capacitors, some in parallel with others, some in series with others, and find a one equivalent capacitance. That'd be an example I would have liked to fit to show you, but I think it's probably better that I at least spent this time so I can at least test you on this portion of the material, which is computing a capacitance starting from calculating the electric field, then calculating the voltage, then calculating the capacitance. So this is something you got to be able to do for the face-to-face test. You will get a chance to, of course, see me on Monday, or for your class, it'd be Tuesday. So you have one more time before the actual exam. You guys are free to go. Thanks for coming. Make sure you put your name in the sign out sheet, and I will email everyone when I actually have the practice face-to-face test up. Thanks for coming, everybody. I'll wait for the last person to leave in case anybody has any questions.
Hey, Professor Younger.
Yeah, Michael, what's up?
So on that previous example with the cable, when you had the natural log of RB over RA, how did you determine that was negative? I
Oh,
missed that
because
step.
gotcha. So my drawing, let me show you the drawing again. That would probably be a little bit easier for you to make sense of. My drawing, I made the radius of the inner wire, the smaller
Mhm.
one. I made that radius RB. So that's a smaller number than is
Yeah.
RA. And when you take the natural log of any number less than 0, you automatically get, or excuse me, less than 1, you automatically get a negative.
Oh, I got you. Okay.
Does that make sense?
Yeah, yeah, that makes sense. And then they're both negatives and they cancel out, so it's a positive capacitance.
Exactly.
Yeah, okay, I got that. Yeah. Oh yeah, man. Sorry, when you called on me earlier, like I'm really weak with like physics too right now. So I've been meaning to study, but I've been busy with my other classes.
That's
You know,
okay.
like back in high school, I had physics C, mechanics, and gen physics, and like that was my favorite thing.
Right.
And but like my calculus was really weak. Like when I did calculus BC or Calc 2, like I was
Uh-huh.
really weak in that. So when I got to community college, I focused more on math than physics. So
Gotcha.
but I've been trying to study and like wrote a textbook. I think like on my Pearson modules, I'm like really behind. I've been meaning to get on those. So I'm
Yeah,
sorry
just
about
keep
that.
your work
Yeah,
up. If you're able to do okay on the tests, the homeworks have a way of fixing themselves. So don't worry too much about that. If you're not, if you're able to do enough work with the practice tests and the chapter practice that I put online, so that you can still get good test grades, then don't worry too horribly about your grades being low in the Pearson online homework. Because really, the whole
yeah.
purpose is to teach you how to succeed on the tests.
Oh yeah, for sure. I like how it kind of goes through like ABC where you have to derive things. Kind of, I really like that. So,
Good.
because for me, I don't really like just memorizing the equation. I want to derive it. So,
Yeah,
um,
that's the holy grail of learning is if you can
yeah,
come up with the arguments to make it yourself, then it's more meaningful and it's not so much memory work as it is at least a
yeah.
narrative that you
Like
have.
I remember in my physics classes in high school, literally like every test kind of I
Mhm.
would just be deriving things because I couldn't remember like exactly the thing. So like that's how
Right.
I went into every question kind of. I was just like writing like random stuff down. So
Well, if you choose to major in engineering or physics, especially physics, there's going to be a time where you might not be able to figure out how to derive it while you're taking
mhm.
the class.
Oh yeah,
Don't
for
let
sure.
that discourage you. That doesn't
Yeah.
mean
That's
anything.
kind of something I'm realizing now, like that's not good for time, you know?
Oh yeah,
So
yeah,
because I saw some video this engineering lady, she's talking about like, in high school, you can get everything like 100 kind of and take your time with it. But when you get into high school, it's about getting it right and doing it quickly, you
right.
know? So
Yeah, and there's
yeah.
a little bit of that sometimes with these tests, especially if you're at a bigger school where, this calculus-based physics class at Chapel Hill when I was there, we had
Hmm.
students that were about, probably 200, 300 students in one room. So yeah, in that case, they want to test you on everything, but they also want you to get it done quickly. So sometimes that will bite you in the rear. If you keep going to smaller
Yeah, for
schools,
sure.
it's not quite so bad, but it could still sneak up on you.
Yeah, because I'm gonna be transferring to Virginia Tech next year. It's definitely gonna be harder there too. And my
Exactly.
differential equations teacher, he's like always talking about that. Like when you go to UVA or VT, like it's a lot harder than this. So just
Yeah,
trying to prepare myself now.
but if you can, if you can make the transition, you'll be much better off for it. So it'll help you in the long run. You'll do fine. I don't have any qualms or worries about your abilities. So far, you've shown us that you're doing, you know
Oh
what you're
yeah,
doing.
thanks.
So
Yeah.
keep it up,
Um,
Micah.
thanks. All right. Oh, also, I missed the lab. Wait, what's today's Thursday? Yeah, yeah. I missed the lab yesterday because I got sick. So,
Gotcha. Yeah.
yeah, yeah. So it was the optics lab. Am I able to make that up on
You actually
one?
lucked out because what I did today was essentially that I ended up because I wasn't quite happy with the status of the lab report the lab that we were supposed to do that day. I
Yeah.
decided to make it 2 hours of lecture material as opposed to
Oh, okay.
lab, so you didn't
Yeah,
miss a
that's
lab at
cool.
all.
I got you. Man, my sister, she like came down with some form of, I don't know, man, some kind of
Something
pathogen. And
something terrible.
she came into my room to use my printer. And then I literally told her, like, please do not get me sick. And she was coughing the whole time,
Ah,
man.
yeah.
I'm like, oh my goodness. Yeah.
That's what family members are good for, man.
Yeah, that's real.
My daughter's
My,
suffering the same thing. She's got some
oh
kind
yeah.
of respiratory thing, and
Yeah.
me and my
Yeah,
wife had
there's
it too.
something going on. Like my circuit theory class, like half of the people were gone on Monday. So
Oh yeah, yep.
yeah.
There's a lot of that going around. So,
Yeah. All right,
how's
but
circuit
thanks.
theory going? You like it?
Oh, yeah, circuit theory. I really like it. So, what is it? We're working on op amps right now.
Oh, okay.
Uh,
Those are tough.
well, I'm trying to remember. Oh, now we're doing the Evan, or I
Thevenin
forgot what it
equivalent,
is.
Thevenin and
Yeah,
Norton.
that's what I missed last class, so we're starting that. So yeah.
Yeah, that's a
Um,
neat little thing. It's called a Thevenin equivalent and a Norton
mhm,
equivalent, and
yeah.
it just allows you to treat every object like it's a power source with a resistor,
Oh, that's
so you
cool.
don't
Yeah.
have to know
I
the details.
yeah, I haven't been able to look at it yet, but I've really liked the math involved in it so far. I remember in high school, I went to Lansdowne High School, and I was
Oh,
in one of
okay.
the academy classes for basically electronics there.
Right.
And we were supposed to go over like the theory of circuits, but we never got to do that. We just did like applied stuff, kind of like we soldered like radios and stuff like that. But I didn't get to know like the theory behind the circuit. So I really like that class
Yeah,
now.
there's some good stuff to learn in there. Simpson's a good book, and Abramowitz, or not Abramowitz, I'm trying to remember the name of it. There's two really good books on that. But one thing we did, for instance, with op amps that you might like is you can actually make an op amp to match a differential equation. And
Oh,
then if you connect the op amps with a voltage source, the oscilloscope will show you the actual graphical solution of the differential equation.
oh,
That's
damn, that's
one of the
that's
cool
weird.
things. Yeah,
That's cool.
you can do integrating circuits, you can do differentiating circuits, you can do adding, subtracting, multiplying, dividing, and from that you can just make up a whole equation and then put in the input and out pops a solution that's actually a solution to a differential equation.
Mhm. Yeah, like right now, my math is really weak with DiffEq, and I know it's really important for like physics. And I'm doing like ECE, so I
Hmm.
really have to work on that. So, I really want to work on it too because the more DiffEq I know, the more I can understand like kind of like what you were talking about, like the oscilloscope and stuff. So,
Right. Yeah,
yeah,
it'll help you. Don't worry, you're way ahead. I mean, if you know anything about differential equations at this point in this course, then you're doing really well. But you're taking differential equations right now, though,
yeah,
aren't you?
yeah.
Yeah, that's a slow process too, because the mathematicians want to teach you everything that you need to know about each particular type, whereas us physicists want you to go through each particular type really fast so that you can have experience with every one. So don't feel bad if you feel a little bit lost. You're going to get a lot more differential equations as the semester or as your career goes on.
I gotcha. Yeah, but
Right.
anyways, over spring break, I'm gonna make sure to study. So yeah,
Yeah.
hopefully when you call on me on the Zooms if I get back from spring break, I can answer some stuff for you. No,
No,
I'm so
no
sorry
problem.
because
I just
I know
appreciate you
I
normally
yeah.
answering for me. I
No, I
figured you
know
were probably
sometimes
being
you're like
quiet because you felt bad about stealing the answers, or
yeah,
not stealing them, but stealing the opportunities from other
yeah.
students.
Because I know sometimes you're like asking and no one responds. It's like, oh, sad younger.
Yeah,
Oh,
I get really sad. I'm like, oh man, come on,
yeah.
because I
Oh,
have
I
so
got you.
much confidence and faith in them, and that it's just sometimes they're not paying attention. Sometimes they're paying attention. They just don't want to say anything. So
Yeah, I got you. It's just with this like my math like maturity is like the foundation is kind of weak, so it's hard for me to derive some things, especially with like this past 2 weeks with
hmm
like the Gaussian surfaces is kind of weird. That's why I have to study it.
yeah,
Sure.
it takes a
So,
little while, and
uh,
actually, you
all right, but
might
anyways,
find it a lot easier to not know the details like what the author gives you. If that's the case, then use that later. You'll make more sense of it.
I gotcha. All right, but thanks, Professor. You have a good spring break.
No
I'll see
problem.
you.
You too, bud. Have a good one. Bye bye. Bye, everybody. This camera picture does not look good. I don't know what's the deal with